So continuing that conceptual build, where we were just now talking about things like how we could take the sampling distribution for proportion and think about it in terms of group data or samples, summary statistics, that p-hat, summarizing different samples and thinking about the fact that we can have some prerequisites to make it normally distributed. And even with X-bar, the idea that when we talk about the groups, the averages for groups of values, that again we start getting things that are normally distributed. As we continue that, we have some conditions to meet. So we begin with conditions. The conditions are to check things like, is our sample large enough? To check things like, is there independence? So there are 3 conditions that must be met. Okay. Condition 1 is randomization. I mean, that's almost always a given for our sampling techniques, right? I mean, that was back in the beginning when we said, hey, do we even have data that is decent enough that we can even look at the data, statistically speaking, or use the data. So data are drawn with a simple random sample, or the sample is unbiased and representative of the population. So data are drawn with simple random sample, or the sample is unbiased. It is representative of the truth. Of the truth of that population. Item 2. We have something called a 10% rule. We need to check and make sure that less than 10% of the population has been sampled. So we want a sample that's large enough but not so big that it begins to mess with some of the theories that we've used in building the way we make inferences. Item 3, success failure. This is the one I put on in the conceptual video already. N times P and N times Q, which you can think about N times Q as being the same as N times 1 subtract P. Remember, that's what Q is, right? These must be greater than or equal to 10. Both of them. Okay? If we meet these conditions, then we are allowed to treat the distribution of p-hat, the sampling distribution for proportions. We are allowed to treat that as something normally distributed. And this right here, if you want to see the proper notation for it, is how we would describe the features of p-hat, the distribution of p-hat. So if these 3 prerequisites are met, what we say is that the sampling distribution for proportions, p-hat, can be approximated with the normal distribution, where P, the true percent, is the mean, and the standard deviation is equal to the square root of P multiplied by Q, both divided by N. So let's practice an example. Okay, example 17.1. It is known that red-green color blindness affects 7% of American men. A school district gives tests to the 233 incoming kindergarten males. Okay, so we want to look at what's going on here. First of all, what is the random variable? Let's label some things from our problem. Maybe that will help it stand out better. Let's see. I'm going to highlight. Remember, this example is in your class notes. That way you do not have to write everything out if you don't want to, if you're printing your notes or saving them with these videos. Okay, so let's see. Color blindness affects 7% of American men. Okay, that looks like a p hat is equal to 7%, decimal form would be 7/100. And I also see here 233 incoming kindergarten males. That looks like it will be my sample size. N is equal to 233. So while we are here, let's also go ahead and write down what Q hat would be. So what's the opposite of that 7%? I'm seeing a 93% if we say 1 subtract 7%. Okay. Random variable. Well, the variable it looks like we're talking about is p hat, right? So our random variable would be that p hat is equal to the sample percent of male kindergartners who are colorblind. Okay. Are the 3 conditions met that we just discussed? Let's see, so going back to the 3 conditions, randomization. Okay, well, in this case, I would say, you know, we don't know a lot about the study that was done, but we have no reason to think that the that the sample is biased or unrepresentative. So a lot of times for condition 1, the randomization, we're looking at where the data came from, and we are also looking and saying, are there any red flags, right? Because sometimes we don't know all of the details, but are there any red flags that would make me think this was a biased or a non-representative sample? No, there's not. So we'll say it's likely fine. Okay. The second condition, let's see, what was that? That was the 10% rule. Okay, so 10%. Do we think that our sample size of 233, that it's reasonable to say that that is less than 10% of all male kindergartners? Because remember, that is our population of interest, right? Male kindergartners. And I would say, yeah, it'd be, you know, that's definitely less than 10%. Condition 3. Do we meet the greater than or equal to 10 criteria when we multiply sample size by each of our probabilities? Okay, so sample size of 233 multiplied by the 7%, sample size of 233 multiplied by 93%. And actually, when you're taking tests and things, if you're checking prerequisites, if you check the smaller one of the two, you're going to have it, right? Because both have to meet the criteria. So this smaller one, the 7%, is at 16 and 31/100ths. So we know we pass. We are definitely bigger than or equal to 10 for both. I mean, if you want to go ahead and multiply the other, let me see what I get. I'm getting 216 and 69/100ths. So both of them definitely pass. Okay, good. Conditions are met. Check. Describe the sampling distribution. So using this notation, p hat being approximated by the normal distribution, where we said that p would be the mean And we said that P times Q, I keep trying to copy exactly from your class notes, and that's actually not the way I usually teach it as far as the notation there. P times Q divided by N, the square root of that is going to be my standard deviation. So in this case, we will use the best information that we have available. I know it came from the sample, but we're using the best we've got. So we will say that for P, we're using that P hat. Oh, actually, that's a known thing. That's definitely the P. Sometimes with confidence intervals, we will use the best that we've got. For right now, though, it looks like we actually had it. It was a known thing. Cha-ching, right? Okay. And because we know the sample size, everything else is known too. So right now, actually, we are totally still being very literal and using the best numbers possible. So let's see. We have that, right, P times Q, over 233. And that number, if you write it out to a lot of decimals, should come out to be something like 0.016715237. That's just taking it out to quite a few decimals. That's my standard deviation. And this is my mean. Okay. Pretty small standard deviation. We are talking about in percents though. This is like almost a little bit over 1.5% standard deviation. Okay, next question, or next part of this example question. What is the probability that more than 10% of these kindergarten males will be colorblind? So, given our distribution here, we said it qualifies as being normally distributed, so I'm a picture person. Let's just make a little picture of what we've just now asserted on the last page. We just now said that my mean, my P, is equal to 7%, or 0.07. We have just said that our standard deviation is equal to, I'll take it to a few decimals, 1.672 if I round to 5 decimals. Okay, and we are being asked what is the probability that in this sample, my P hat from the sample, that it will be more than 10%. That it is greater than, we're treating it continuous, so you can say greater than or equal to if you'd like, 10%. What's the likelihood that I get that? Okay, so on the picture, this is not drawn to scale at all, but we're looking for P hat equal to 10% or greater. And again, it might be a whole lot more of the normal curve. I'm just giving you a depiction of what this thing looks like. Okay, so let's use StatCrunch to help us get this. Because we qualify for the normal distribution, we will go to calculators. We will go to normal. Okay. The mean, we said 0.07. And I would go ahead for standard deviation and use as many decimals as you can, because StatCrunch doesn't typically play very nicely with fractions. Usually it won't take fractions. So I'm going to use all the decimals that I gave you all. 0.167, 1.5237. And probability greater than or equal is what we were asked. And then 10%. Remember, everything here is in decimal form, even though I'm saying percents out loud. Okay. And it looks here like about, what, a 3.5% chance that the true proportion of colorblind male students, or excuse me, that the sample proportion that we get out of this group would be more than 10% of them. What is the probability that fewer than 5% would be? Okay, so notation-wise, the probability that my sample percent is less than or equal to 5%. Remember that what's going in the parentheses when I'm using StatCrunch, this is my x-axis. Whoops, that looks bad. This is whatever's on my x-axis, right? So this right here is the sampling distribution of p hat. My x bar is talking about proportions. And it's sampling distribution proportions going along that, right? So that's why inside we have p hats, because that's what we're talking about. That, in fact, maybe to help you remember, that's what's on the x-axis, or in this case p hat axis, right? Go back and recall this, that random variable. That's what you're putting on that horizontal axis, the p hat. And that's what's going in parentheses when you're finding those probabilities. Okay, so let's try it. Everything stays the same except we're saying less than 5% in decimal form. And it looks like this time we're getting about 11.5%. And again up here, this was about 3.63 or 3 63/100 in percent form. Okay, what is the probability that between 8% and 12% will be colorblind? Notation again, the probability that p hat, always point your arrows to the left when you're sandwiching them for an in-between probability, that p hat is in between 8% and 12%, still in decimal form. Let's use between on the normal calculator. Okay. We'll say it's about that, so it's approximately 27 and 34/100 of a percent. Or percent. It's not of it because it's 27%. And then a little bit over that. Okay. What is the 75th percentile of the percent who are colorblind? You know, let's sketch that picture again. I'm actually going to see if I can copy it over. Let's see if I can remember how to do that. Oh, it's that one. Okay. Okay, so we still have the same distribution. That's what I wanted to show you. Of course, this time we are not actually looking for the probability or the percent under the curve given a p hat. We're actually working in an opposite direction, right? So with this right here, we are being told that we care about having 75% under this curve. Remember that percentiles, any aisle, I-L-E, right, percentile, quartile, decile, any of those things would be always considered cumulative percent to the left. That's how those play. So right here, what we are saying is, okay, 75% area to the left of something. We don't know what the something is. What is the p hat that would give me 75% to the left? Okay. So this time our notation would look different in the computer. Let's go over here. So I'm going to go back to standard. I'm keeping all of my attributes the same, means the same, standard deviations the same. And we want our area point to the left. This is a percentile. We know they are always cumulative, area to the left. And I want not there, because remember inside the parentheses with that inequality symbol, that's for when I know what's on the, I keep calling it x-axis because maybe that helps you, the horizontal axis, in this case for our random variable p hat, that axis. That's for the number on that. We don't know that number. There's a question mark up here on our picture, right? We do not know the number on the axis. So let's go to the outside, because we do know the percent under the curve, the probability that we're looking for. We're looking for 0.75 or 75/100 in decimal form. And there we have it. It looks like a p hat equal to about, what, 8%, a little bit more. About 8%, approximately. Okay, so that means that about 75% of the time, we will have equal to or less than 8% of our group of males being colorblind, male kindergartners being colorblind. How many standard deviations from the mean would an unusual observation be? We actually had 2 tiers of unusual in this class. We talked about unusual versus very unusual. Unusual, we always said, was actually 2 standard deviations. But here, for very unusual, I want to emphasize that more than 3 standard deviations is considered very unusual. Okay. And so you could figure that out. Let's take our little decimal here, 0.01672 multiplied by 3. If you add and subtract this number to the center one, to that 7%, you'll know the cutoff points for what would be unusual. So let's do it. Let's add and subtract 3 standard deviations to that 7% and see what we get. So 0.07 subtract, I'm going to say second answer on my fancy calculator. I'm getting a low end of about almost 2% actually. Okay, so that's anything below about 2% would be considered very unusual. Anything above, let's go back. This is what happens when I choose to be lazy here. Okay, we'll scroll into the memory of my calculator to get the values back. 0.07, subtract my answer. I had to redo that answer to make sure it would do it right. Ah, no. I meant to say plus, because I'm adding this time. So 7% plus that small decimal there is going to be about 12%. So above about 12% will also be unusual. Very unusual, excuse me. We did use the plus or minus 3. Can you cut the standard deviation in half? Well, I mean, I don't know. Let's look at something. Let's look at how do we calculate the standard deviation here? Standard deviation was equal to the square root of P times Q times N. So if I wanted to make some change to this number, without lying about the truth, without lying about the actual true probability of colorblind male kindergartners and the true probability of not being a colorblind male kindergartner. So I can't change P and Q. The only thing I have control of in this context right here, or at all with standard deviation, would be sample size. So what I want you to consider is what would you have to do to the sample size to get 1/2 the standard deviation? And maybe a quick little algebra trick would help us think about it. If I want 1/2 of, I'm going to 1/2 times standard deviation. Remember, just basic algebra, when we have equality, we have to do the same operation on both sides of the equal sign to keep it true. So I'm going to say 1/2 times on the outside there. That keeps my equality true. So let's explore that more. Okay, 1/2 times this square root. Now what if I wanted to put that under the square root bar? Can we work backwards? What up under a square root bar would be the same thing as 1/2? I guess if you know that a square root means that you're saying what squared, then you know that square something to put it back under. See, look. 1/4 multiplied by standard deviation. Wouldn't that be the same as 1/2? And if you notice that, well then remember when you have radicals attached by multiplication that you can actually put the stuff under the radicals together, right? So this will be equal to square root of P times Q, and we have 4 times your sample size. Okay, so to cut standard deviation in half, you need a sample size that's 4 times as large. And the big concept there being the controllable thing here that will control your picture, the consistency, the standard deviation of that picture is the sample size.